Hello, I'm Kiran Kumar from Nature of Physics. Today topic is hysteresis, cycle of magnetization, retentivity, coercivity of a magnetic material get magnetized in a magnetic field. Please watch previous videos. Part 1 is magnetic field intensity, part 2 is intensity of magnetization I, and part 3 is magnetic susceptibility Xi, and this is the part 4 video, student. Then only we can clearly understand this video, student. Please do like and subscribe. Please watch full video, you will get clarity about the concept, students. So hysteresis, the logging of intensity of magnetization I and magnetic induction Bm behind the magnetic field intensity H when a magnetic specimen is subjected to cycle of a magnetization is called hysteresis, student. So cycle of magnetization, when a ferromagnetic specimen is slowly magnetized, the intensity of magnetization I varies with the magnetic field Bm. Through a cycle is called cycle of magnetization. And here there is a solenoid which is connected in the closed loop with the battery, student. Whenever current passing through the conductor, magnetic field produces in the conductor. The magnetic field used to magnetize a material, student. First considering this is the unmagnetized material, domains are randomly arranged in all directions. Whenever the unmagnetized material kept in the uniform magnetic field of a solenoid, inside the solenoid the magnetic material get magnetized. So there are two values are there, student. One is B0 and another one is Bm. B0 is the magnetic induction of the solenoid, air as a medium, and Bm is the magnetic induction of the material, student. B0 is equal to mu naught H, student. B0 directly proportional to H. H is the magnetic field intensity, student, and Bm is equal to mu naught I, and Bm directly proportional to I. I is the intensity of magnetization. Next there is a graph between the IH, student. I is the intensity of magnetization, H is the magnetic field intensity. So that in the graph at the origin 0, 0, 0, so all the coordinates are 0. That's why intensity of magnetization and magnetic field intensity all are become 0 at the origin, student. Okay, so this is the point 1 is representing, and point 2, that is OA representation, student. So that at a point saturation magnetized, that is H increases, I also, because of H is directly proportional to current, student, that is free current, previous video I gave, and I is the intensity of magnetization and Bm is the magnetic induction of the material. Here H increases, current also increases, and intensity of magnetization increases with increasing the magnetic induction of the material. Okay, student. And then continuation, third point is there. Third point representation, this is at a point A, student. A represent what is that? O to A. Okay, and next point 3 is representing from A point to B point, student. From A point to B point, here H value is decreasing. See, H is decreasing, nothing but current also decreasing, student, and I is the intensity of magnetization also decreasing. See there, clearly appearing decreasing. That's why Bm also decreases. Simply remember, H is depend on the free current and Bm is depend on the intensity of magnetization. The graph is between I and H, student, clearly given. Okay, and next one here two values we have. One is the retentivity, another one is the coercivity. Retentivity represent O to B, student, clearly represent R is the retentivity, and coercivity is represent OC, student, along the negative x axis, that is OC representing coercivity represented by letter is C, student. Okay, retentivity is represented by letter is R, student, and it is defined as the intensity of magnetization I remains in the substance when the magnetic field intensity becomes 0, student. Along the y axis x coordinates are 0. There is a point B, student, at which intensity of magnetization is remains in the substance, but magnetic field intensity is equal to 0, H is equal 0 when I is present. This is representing the retentivity OB in the diagram. Okay, and this is a hysteresis loop, student, closed loop, and clearly the values also represent at a point B. H is equal 0 and I also 0, H directly proportional to I, and I not equal to 0, nothing but BM also not equal to 0, student. Okay, next one is coercivity, that is representing OC, student. It is the amount of magnetic field intensity H required to demagnetize a material. For this, H is not equal to 0 along the negative x axis. H is taken as negative, student. Okay, and whenever H not equal to 0, I also not equal to 0, student, but along the x axis, negative x axis, y coordinates 0. So I, capital I, is intensity of magnetization 0 and BM also 0, student. Okay, there is a clear relation that we did about the hysteresis, cycle of magnetization, and retentivity, and also coercivity of a magnetic material. 1 second. Yes, student, continuation here. Hysteresis loops are curved, student. So in this, the curvature represent the relation between BM or I of a ferromagnetic material with a magnetic field intensity H, student. Relation between I and H graph representation is known as hysteresis loop, student. Okay, the area of the hysteresis loop is directly proportional to the energy wasted per unit volume of a material, student. Okay, for each cycle of magnetization, first A position is the magnetization, student, and next C position represent the demagnetization, student. After that, D position represent the magnetized but opposite direction, student, opposite direction. Next, D point to F point is demagnetized. From F point to A point, again magnetization. This is the curve, student, that is a closed loop. We are getting first magnetized, next demagnetize, again magnetize, and again demagnetize, then magnetize, student. Uses of this hysteresis curves is to find saturation and retentivity and coercivity, student. And next, permanent magnets, examples galvanometer, voltmeter, ammeter, and second one, an electromagnetic core, transformer core, dynamo core, and choke coil also we are using this phenomena, student. And there is a difference between the steel and the soft iron. Hysteresis loop of a soft iron and steel going to discuss, student. The retentivity of a soft iron, the retentivity represent what is that, student? OB. See, I wrote OB retentivity, and OC represent coercivity. These values are common for the both diagram, steel and the soft iron of the hysteresis loop of a magnetic material. OC is the coercivity and OB is the retentivity, clearly represented all the values, student. So that the soft iron is more stronger than the steel. Soft iron, what is that, student? More stronger than the steel. Reason is soft iron has the more retentivity comparing to the steel, clearly appearing the difference. See there here. And next, coercivity of a soft iron is less than the coercivity of the steel, student. Coercivity is less for the soft iron comparing to the steel. Okay, that's why the soft iron loses the magnetization more rapidly than the steel, student. Okay, and continuation, next one is the area of IH loop of a soft iron is smaller than the steel. So hysteresis loss of soft iron is smaller than the steel, student. So clearly represented about the hysteresis loop of a soft iron and steel, student. For my work, for my writing, please do like and subscribe my channel Nature of Physics, our channel. Thank you, students.